Very good. Hey, hello, how are you?
Hey, and
Okay, so you are the fourth presenter, right?
yeah,
Very good. Do you want to try a, we're recording, it's automatically set to record, so it's okay.
yeah,
It doesn't matter. We're starting at 3 o'clock. Do you want to try sharing the screen, see that everything is going well?
yeah.
Okay, I'm gonna stop sharing. Looks good.
Is this visible?
Yeah. Mhm.
Let me just put into the play mode and see that whether the cursor and everything is visible.
Yeah, this one looks good too. I mean, it looks better than the other one, but they both look good. This one is obviously the presentation. Excellent.
Okay. Yeah.
Hello, Aaron.
Hello.
Good to see you
Yeah,
here.
thanks
So
a lot.
we are recording, but it doesn't make any difference.
Yes.
3 o'clock, we're gonna get started, but let's see. Do you want to try sharing the screen to make sure everything is good?
Yeah, let me do that.
So Abhishek is number 4, and you are number 3. Oh, looks good. Mhm.
Okay, perfect.
Let me see if I have any questions. I got your answers. Do I say Levi Lab or Levy? Levy.
Yes, Levy.
You
Sorry,
got
I was
it.
muted.
But you said Levy.
Yes, Levy.
Okay. So then Akash, how are you?
Hi, doing well. How are you doing?
Okay. Good to see you here. So you are number 2, the second presenter today. We are recording, but that's because I'm not a host, but it's set to record automatically. So it's good that you guys are here early. Akash, do you want to try sharing the screen so we can tell you that everything was good?
Yeah, sure. Let me do that.
So it's Akash Dixit, right?
That's right.
Perfect.
Okay, let me go to this mode. And which screen are you seeing in this case? My notes or the slides?
The notes.
I see. That looks like the notes, correct?
Okay, so I'll flip them then for the actual.
Uh-huh. Okay. So this, and now we're waiting for Avinash, and then of course for everybody else.
How are you guys? Hi, this is Abhishek.
Hi.
And there's Avinash. How are you? So Avinash, I say Rustagi or Rustagi?
Rustagi.
Okay. Thank you so much. It's recording because automatically set to do that, but our event starts at 3, so we have 7 more minutes. People usually come last minute, which is fine. We're going to stay in the recording. We've changed a little bit of the schedule last time. So the goal is, first of all, we are very grateful to you, that all of you, that you came here and you're presenting. And we want your work to be sort of rewarded in some sense, at the very least, with attention. But attention in the sense of our goal would be for the industry member to sponsor you in some sense, in being interested in your work, and for the work to receive the appropriate kind of attention. So here's our director, Celia.
Hi, everyone.
Also just joined.
Right.
I was saying that although this is being recorded, we changed the format a little bit last time. So the plan is for everybody to have 15 minutes of presentation. That makes an hour. And then we'll have hopefully 20 to 30 minutes of discussion in which you could ask any questions. We could, I guess, connect you with industry partners that want to participate, and then see if we can give you points of contacts in industry and follow up with you later as a result of this set of presentations. We'll see how that goes.
That sounds great.
Yeah, it's a nice chance to have the sort of informal conversations that are hard sometimes in these.
Yeah, thanks a lot for this opportunity.
Great to have you all. I commend you for volunteering. We really appreciate it, and everybody's very busy, so we never know, what kind of audience we'll get. And in fact, I'm going to have to jump off in the middle of this, so I won't be there for the discussion at the end unless my other meeting ends a little early. So just wanted to be here for the kickoff at least. And Adrian, I don't know if you want me to welcome. I think you can handle it. I don't need to be on the agenda at all, but whatever works for you.
Yeah, it's whatever you want. It's a tight timeline, and I have I asked them some questions, and then I'm going to introduce them, and that's going to take some minutes. So
I say you take it from the top.
Yeah. So Avinash, I don't know, I just can't remember. Did we tried with the other three presenters. Did we try to check that sharing of the screen works?
We did not.
Okay, so I'm going to stop sharing, and why don't you take the screen?
Yeah. Can you guys see my screen?
So if you switch into a slideshow.
Yeah, sure.
Perfect.
Oh, that looks good.
All right.
So we have a lot of people coming to these meetings. We have some recordings online. Let's just, I know it's not going to be like this, but let's just assume there's just the 6 of us. Let's just pretend that. You should go, this is recorded, right? So it's going to be distributed. It's not going to be just the 6 of us, but pretend that. You should just go on as if you're on TV, right? Knowing that you're going to have an audience of however many later in YouTube, okay? Because what I'd like to do is I'd like to start at 3 o'clock, given the time frame, regardless. Be interesting.
Well,
we had a.
It's hard because everybody has back-to-back meetings, so we know that people will join, 3 minutes late, maybe 5 minutes late. So I don't know, Adrian. If you want to, especially if you're planning to keep the mic open after the end of the hour, you might wait just a couple minutes for people to join. But all they'll miss is your introductions.
True.
What is that purple thing behind you?
Is that what?
What is that purple?
Just kind of.
This, a student of mine did this.
Oh.
So I bought it. I bought it and I put over here. Yeah, it's chess pieces.
Chess pieces. Right? Yeah.
That's pretty good. Okay. She had another one. So I teach a web class, a web development class, and she put together a shopping cart, and then she put her paintings in. And I said, well, what paintings are these? And she said, these are mine. And have you sold many? And she said, one. Oh, darn. So then she showed me what she had, and I bought two of them because they were very good. I mean, I like this one very much.
That's nice.
That was in spring, this spring.
Jen Robinson, she's with the Army, actually. Hi, Jen. Nice to
Hello.
meet you.
Hello. Okay, I'm going to share the screen.
Adrian, I think I will go ahead and make you the host since I have to leave early. I know Crystal has conflict also, so I think just for safety, it's probably best for me to make you the host or the co-host.
Okay. If
I
I'm,
can.
yeah. Yeah, so people are joining. What we want to avoid is the real host leaving and then the meeting collapses or the recording stops.
Yes,
And
I
then at the end,
understand.
I suppose,
I think Mary set it up to record to the cloud. That's, we'd had some conversation before the meeting to make sure that it would be recorded properly. So I think it's all
I
set.
came a little bit early. Yeah, yes, I came a little bit early and it's recorded immediately. So I'll ask her to get the recording at the end.
Okay.
So should we get started?
Sure. I see people are
We
starting.
have 14 participants, 15 now, so people are joining. Okay. So I'd like to welcome everybody to the QED-C Student Research ePoster session. Our TAC, Workforce Development TAC, is sponsoring this event. Today is June 22nd, and it's now 3 p.m. Eastern. The slides that I have over here, I want to point out that this particular type of session started almost a year ago, a little bit more than a year ago. June 16 is when we had the first session. And you can see the URL at the very top, and that's the plan for today. There are 4 presenters. We are extremely grateful to them for being here today to talk about their research with us. And I'm going to introduce them in order. We are on a relatively tight timeline here schedule, but I did ask them some questions and they sent me some answers which I'm going to use in the presentation. So I have a bio and for each one of them, and then I have a question that I asked all of them following Jim Freerich's approach in some of the courses that I've seen online. He says that at every exam, PhD, he asked the question, how could you describe your research in a way that a high school senior could relate to? And I asked our presenters today to do the same thing. I also did something that I haven't done before. I asked them to enumerate top 3 employers, dream employers. We shouldn't read too much in this, but I want to get some sort of reaction from the industry partners. So they mentioned some companies, and let's see what that means. Our first presenter is Avinash Rustagi, who is a postdoctoral research associate in the Department of Electrical and Computer Engineering at Purdue University. Before joining Purdue, he was a postdoctoral research scholar in the Department of Physics at North Carolina State University. He earned a PhD in physics at in 2016 from the University of Florida. Currently, his research interests include hybrid quantum systems for sensing and information processing application spintronics and magnonics. I'm going to let him start, and in about 12, 13, 14 minutes, you'll be able to ask questions. So Avinash, take it away.
Thank you for the kind introduction. Is my screen visible? Okay.
Yes.
Thank you. So thank you for this opportunity. Today I'm going to present one of our works highlighting the role of chirality in quantum impurity relaxometry of magnons in ferromagnetic thin films. This work was done in collaboration with Jacopo Bertelli and Toeno van der Sar from Delft, and my supervisor here at Purdue, Pramay Upadhyay. And this work was supported by the Quantum Science Center and by NSF. So when we think about a ferromagnet, we visualize a collection of spins or magnetic moments which are connected by ferromagnetic exchange couplings, which suggests that these magnetic moments are co-aligned and prefer to be aligned in the same direction because that lowers its energy. On top of this ground state configuration, you can have excitations of a magnet, which are essentially wave-like excitations called spin waves, which could be a finite wavelength. A special class of this excitation is called the uniform precision mode or the ferromagnetic resonance mode, which is nothing but infinite wavelength scenario of the spin waves. So all the magnetic moments precess uniformly in a coherent fashion. The quanta of these spin waves is what is referred to as magnons. And these magnons are particularly promising when it comes to designing next generation classical and hybrid quantum technologies. As an example, there is the field of magnonics, which aims to utilize magnons as information carriers. On the other hand, you can have hybrid systems where magnons have been shown to mediate coherent control of a distant quantum spin. So the idea here in this work was that there was a microstrip line which was used to excite magnons, and these magnons propagated within the yttrium iron garnet ferromagnetic thin film and was able to drive a distant nanodiamond which contained a quantum impurity spin. At the same time, there are other propositions made where these magnons can be utilized to coherently couple two quantum spins, and that can be scaled up as we move on. So it's very important for these fields to develop sensitive probes to understand the dynamical properties of magnons. This is where quantum impurity relaxometry comes in. The idea here is that you can have a quantum system, which can be a two-level system or a few-level system, and this quantum system couples to its environment. Now, because of this coupling to its environment, if we have an initialized quantum system in some particular state, and there is magnetic or there is noise present in the environment, then this noise will cause relaxation of this initialized spin state. For the case of quantum impurity relaxometry, we can have quantum impurity spins, an example of which is nitrogen vacancy center in diamond, which I'll detail out in the next slide, can be used, and these quantum impurity spins carry magnetic moments, so they are highly susceptible to magnetic fields. Thus, they have been utilized a great deal in sensing magnetic phenomena. And the idea for this relaxometry measurements is that thermal fluctuations can excite magnons in a ferromagnetic material. These magnons will generate gigahertz magnetic noise, which can then relax an initialized quantum impurity spin state. Now, this relaxometry method has been used for a variety of probing scenarios where they have been used to probe magnons in a ferromagnetic thin film, as well as measure magnon chemical potential. Now, as highlighted here, this quantum impurity spin has 3 levels. So there are 2 relaxation rates associated with the pairs of 2 levels here, and which was then measured in these experiments. So what was done here is, while these measurements were performed, there was a lack of theoretical understanding. the theoretical understanding so far that we had was able to only produce qualitative agreement to the experiments, but not quantitative. So in this work, where we decided to take a closer look at the theoretical formalism and come up with a quantitative model that explains all of these measurements. Before moving on to the details of these, let me first quickly, briefly summarize to the audience that are not familiar about this quantum imperative spin, specifically the example of nitrogen vacancy center endiamond, and go over some of its basics. So nitrogen vacancy center endiamond is a substitutional defect where one of the carbon atoms is substituted by a nitrogen and its adjacent site is a vacancy. In its charged state, this vacancy can trap an additional electron such that this entire defect system behaves as a spin-1 system. As we know from basic quantum mechanics, a spin-1 system can have a singlet or a triplet state. And as it turns out, the ground state configuration of the spin-1 NV center is a spin triplet state, as shown here. This ground state triplet can be described by a minimalistic Hamiltonian, which has this first term, which is the zero field splitting term, since this defect lies in a crystal environment and there is also the presence of spin-spin interactions. And the second term here shows the coupling of this spin system to magnetic fields, because spins are nothing but angular momentum which carry magnetic moment. Now, furthermore, what's important is that these spin states fluoresce, which means that green light is absorbed and red light is emitted. For instance, if we are in any of these states in the ground state triplet manifold, we can absorb green light and go to the excited state triplet, and then it can relax by emitting red photons. Now, further, what is more important is that the zero state fluoresces more compared to the plus minus one states, which means that if we are in this, which essentially is a consequence of the fact that if we are in the zero state, we excite to the excited manifold and we relax back to the zero state. However, if we are in the plus minus one state, then it also can get excited to the excited triplet state and relax to the plus minus one state. However, there is a presence of this additional non-radiative pathway, which allows this state to relax to the zero state as well. Thus, there are less photons that are emitted if we are in the plus minus one state compared to the zero state. Now, this allows us to optically initialize the NV center to the zero state, because even if we started with the plus minus one state, there is a finite probability that it can relax back to the zero state through this singlet non-radiative pathway. At the same time, this also allows optical readout of the state of the system, because the photoluminescence that is observed in the fluorescence is spin dependent. Now, we can also further apply a DC magnetic field, which can lift the degeneracy between the plus minus one states. So because of the zero field splitting term, at zero magnetic field, our zero state, ms equals to zero state, is at lower energy compared to the plus minus one state, which are degenerate. However, if we apply a DC magnetic field along the quantization axis, we can further split these levels and lift the degeneracy. This allows us to create effective two-level system, which can work or which can operate as a quantum bit. Now let's focus on what we can understand from this basic. Where does chirality enter into this NV? If we focus on the zero field splitting term, we can rewrite the zero field splitting term as the spin multiplied by a spin dependent magnetic field, which suggests that if we are looking at this two set of effective two-level systems formed by the zero and the plus one state and the zero and the minus one state, the internal built-in field is pointing in opposite direction. So if we start with a state vector, which is close to the, let's say, the zero state, it precesses around this effective internal magnetic field. And it precesses in opposite directions because the direction of the field is opposite. To cause transition from one state to the other, we'll need to apply a rotating magnetic field in the plane transverse to the quantization axis. And this rotating magnetic field needs to be with the same frequency. Because once we apply a rotating field at the same frequency given by the splitting, we can move to a rotating frame, where this state vector is static and it sees a static magnetic field and thus starts to precess about it and thus causing change in the population between the states. So this is how chirality enters at the level of the NV center. The zero field splitting introduces an intrinsic chirality to the NV centers where oppositely polarized magnetic fields couple to different two-level systems. But this is not the entire story. There's also chirality that is associated with the nature of magnons. Our goal here is that we have a ferromagnetic thin film and we have proximally placed an NV center above the film. So to evaluate the magnetic field coming about as a consequence of the magnetization dynamics, we can calculate that using Maxwell's equation. We note that this right-hand side appears like the Gauss's law of electrostatics, where we have a charge, and this magnetization profile or texture behaves as a charge. Now, since we are focusing on a ferromagnetic thin film, there's a magnetization variation within the plane of the film. However, it is confined along the thickness of the magnet. And when we make a substitution here, we get two kinds of charges. One is a volume charge, and the other is the surface charge originating at the interfaces along the thickness of the film. So what we can do is we can look at how this charge behaves if we look at a schematic of two magnons, one which is propagating to the left and one which is propagating to the right. If we look at this charge if we look at the volume charge in the Fourier domain, we know that this gradient gets converted to the wave vector, and thus this volume charge changes sign depending on whether you are looking at a right propagating magnon or a left propagating magnon. However, the surface charge does not depend on the direction of the wave vector. So in one case, we'll have both the contributions from the volume and the surface charge adding up, creating a larger amplitude of field. And at the same time, the sense of handedness of this magnetic field generated by a left propagating magnon is clockwise. And we have seen earlier that these clockwise magnetic fields will only couple the 0 and the -1 levels. On the other hand, if we have a right propagating magnon, these two contributions offset each other to an extent such that the amplitude of the field is small and the sense of rotation is also opposite and couples only the 0 and the +1 levels. Thus, we can conclude that oppositely propagating magnons generates dipolar magnetic field at the NV with opposite handedness and different amplitudes. To capture all of this, we look at the different sections of our hybrid. First, we have the ferromagnet, and whose dynamics can be described by the Landau-Lifshitz-Gilbert equation, where we have the presence of a stochastic thermal field because this is a thermal equilibrium. These magnetization dynamics can then be translated using Maxwell's equation solution to fluctuating magnetic fields at the quantum impurity, which in our case is the NV center. And once we know the fluctuating fields at the NV, we can use Fermi's golden rule to calculate the relaxation rates. This theoretical formalism, which captures all this chirality, is what we refer to as chiral theory, which captures both the bulk and surface magnetic charge contributions, as well as the chirality at the level of the NV center relaxation rates. Now, the first step we did was to benchmark our theory against the experiments that were present. So we looked at the literature and we found 3 experiments, which was done with different magnetic materials. The first one was using the magnetic material of permalloy, and the other was yttrium, yttrium iron garnet. And the third one was again permalloy, but in this case, the height between the distance between the ferromagnetic thin film and the NV center was a variable. So when we compute in this shaded line, we compute using a theoretical formalism, we get excellent quantitative agreement with experimental measurements without using any sort of scale factors or anything. So this puts confidence in our theory that we have captured all the important physics into the problem, But that was not all. Our goal here was to definitively say that we have come up with a theory which captures this chirality at the level of both NVs and magnons. So to do so, what we did was we created a plot between the difference of the relaxation rate between the two levels as a function of external magnetic field, but we treated the different magnetic materials through its variation of saturation magnetization. So the experiments that were performed were on Ig as well as permalloy, which falls here on the y-axis. And what we could conclude simply from this is that we note that because the amplitude of the fluctuating magnetic fields is larger for left propagating magnons, for small values of magnetic field, we know that the relaxation rate gamma minus will be larger compared to the gamma plus state, which is what is expected and which is what we get in our simulations. At the same time, if we keep on cranking up the external applied field, we make the magnet more and more rigid such that it does not fluctuate that easily, which essentially corresponds that we are shifting the magnon bands to higher and higher frequencies. So after a certain point, what will happen is that these magnon bands will shift out of resonance compared to the -0, -1 level, but it will still be in resonance compared to the 0 + 1 levels. So there will be a rate crossover where delta gamma changes or gamma minus is greater than gamma plus at smaller fields, but the trend reverses in the higher field. So this is what's one particular signature that we wanted to see in an experiment. To do so, we again got back to our collaborators at Delft, who chose nickel, which has a saturation magnetization of 400 EMU per cc. And what they did was use this material and experimentally measure the relaxation rates. And we indeed see a crossover between the two relaxation rates, which confirm that chirality is very important when analyzing these experiments. So I want to conclude by suggesting that we hope to have conveyed to you that both chirality plays an important role, both at the level of NV and magnons in constructing a quantitative theory, which was proposed and verified by new experiments as well. At the same time, this opens up new avenues where quantum impurities can be used to probe chiral interactions and chiral phenomena, as well as engineer non-reciprocal coupling between quantum impurities mediated by magnons. Thank you. I'll take any questions.
Thank you for this beautiful presentation. I just wrote in the chat that if you want, you could ask the questions in the chat, then I can read them, or you could just talk. Whoever has questions can just speak up. If you need to be unmuted, let me know. Let's hear the questions. If for some reason we do not have any questions, I just want to remind you that I asked every single presenter to name, just for the fun of it, the top 3 dream employers. So Avinash has politely not named any employer. He said, I'm very much interested in the research and development that is carried out by the industrial partners. It's very important to buy into the vision of the company and be able to contribute towards that with my skills and experience. Given the extraordinary amount and range of work, it's hard for me to enumerate 3 companies. However, he has 2 questions for our industry partners, and the format is such that we now have 90 minutes as opposed to what we used to have in the past. So we went slightly over the 15 minutes. Let me mention his questions and we can talk about them perhaps in that part at the end. So question number 1 was, what pathway do the industrial partners have for postdocs to transition into research and development of their companies? And the second question, are there postdoctoral research positions at the companies? So maybe we can discuss them next time. So again, if anybody has any question, this would be a good time to ask. Otherwise, I'm gonna thank Avinash for the wonderful presentation, and I'm gonna move on to the second presentation.
Thank you.
Nice job.
Our second presenter is Akash Dixit. He's a PhD student working with Aaron Cho at the Fermilab and David Schuster at the University of Chicago. He builds superconducting qubits and couples them to 3D cavities to develop novel quantum architecture and search for dark matter. Akash is passionate about music, enjoys biking by the lake and playing basketball. For everybody, I asked the question, how would you describe your research in terms that a high school senior would be able to relate to? And this is Akash's response. We can see the effects of dark matter in the universe all around us, but we still do not know what it is. One compelling hypothesis is the very light particles that are washing over us like waves. We think these particles could very rarely turn to light. We build cavities, shiny boxes to capture the light and use superconducting quantum bits to sense the presence of extremely small amounts of light. His dream employers, LBNL, IBM, and AWS. Take it away, Akash.
Thanks very much. That was very off the cuff of a response, so it's not very serious either. But, thanks for having me, everybody. Let me share my screen here. Okay, let me know if you can see this.
Yep, looks
yes.
Perfect. Okay, let me tell you a little bit about our work searching for dark matter with superconducting qubits. I work with a bunch of great people, postdocs, grad students, my advisors, Aaron Cho and David Schuster. Okay, so probably many people are not familiar with the field of dark matter, so I'll give you just the one slide intro about how I think about it. So we obviously know there's dark matter and we know there's a lot of it. And there are two different fields of thought or two different schools of thought. One is these heavy particles and the other is the thing that I work on, which is very light particles that sort of act coherently together. Two of the main hypotheses for what this dark matter could be are these things called the axion and the hidden photon, but the details don't really matter in this particular instance. The main thing that matters here is that we think these particles could potentially convert into light, specifically into a microwave photon, but very, very rarely. You can see I've written the signal strengths here and they're extremely small. The way we try to detect these microwave photons is to use a box, so a shiny box in our case, made out of aluminum or copper or some sort of very high quality material. And then we want to detect the signal that it resides inside of this cavity. So on the left here, I've shown a picture of the traditional way of detecting a signal inside of a microwave cavity. And that is to try to detect both the in-phase and out-of-phase quadratures of the field inside of the cavity. This is like trying to detect the position and momentum of a harmonic oscillator, right? It's something where we know there's a fundamental limit to how well you can know both of those pieces of information. And this is a manifestation of what we call the standard quantum limit. And effectively, this means that there's always going to be about 1 photon's worth of noise just from our inability to resolve both of these incompatible pieces of information. And when you see that there's 1 photon's worth of noise, this is a little scary to us because the signal that we're looking for is much smaller than this potentially. And so we need to come up with a new way of trying to detect these extremely small signals. And the way we've thought about doing it is rather than measuring these incompatible pieces of information, just measure 1 piece of information. And in this case, that's the amplitude of the field, or equivalently, the number of photons in the field. Of course, when you measure one thing with very high precision, you give away information about another variable. And in this case, that's the phase of the field. But that's okay with us. We're okay giving up that information as long as we have very high precision on exactly how many photons are potentially deposited by the dark matter inside of our cavity. So how do we go about building one of these photon counting devices in the microwave regime? And the way we do it is we have what we call a storage cavity. This is what accumulates and stores the signal deposited by the dark matter. We use a transmon qubit. This is a superconducting circuit to sense the photons in this cavity. And then we have some auxiliary readout cavity. This is kind of a 3D sketch of what this whole thing looks like. And here are a few pictures of what a transmon qubit looks like. And this is a zoom in of the main component of that qubit, which is the Josephson junction. It's one of these extremely small sandwiches of superconducting material, dielectric and superconducting material. Okay, well, one thing I didn't mention here was the Hamiltonian that describes the system contains some term related to the cavity, some term that's related to the qubit, and an interaction that we're allowed to engineer based on how we fabricate this. And this interaction has some energy scale 2 chi, but then contains the number operators of the cavity and the qubit again. So I've suggestively written this interaction term here with the qubit. And what you notice is that the transition frequency of the qubit, everything in front of this sigma z, is a function of the number of photons, A dagger A, inside of the cavity. And you can see that here in the data where the peaks of the spectra represent the transition frequencies of the qubit, and they peak at there being 0 photons, 1 photon, or 2 photons in the cavity. And so now the problem of detecting photons in the cavity just becomes a problem of measuring the transition frequency of the qubit. And we do this using a Ramsey type interferometry measurement. I won't go into too many details about that, but we test this out by preparing the cavity with 0 photons and then also preparing the cavity with 1 photons. And in most of the cases, we get it right. We measure 0 or we measure 1. But occasionally, a few % of the time, we get it wrong and we have false negatives here and false positives here. And these false positives are especially bad for us because you don't want to claim that you've detected the dark matter when in fact you've just made an error with your detector. And we kind of understand what the source of these errors are. Your qubits get excited spuriously, and those produce these false positives. So we need to come up with a way to mitigate these types of detector-based false positives. And the way we do that is, again, going back and looking at the Hamiltonian that we've been able to construct and noticing that the interaction term that we're using to make the measurement is really just a product of the number operators, and therefore it commutes with the rest of the Hamiltonian. And what this means is when you make a measurement using this term, you project the state of the cavity back onto one of the eigenstates it already wanted to be in. And we call this a quantum non-demolition measurement, meaning that the photon that we're trying to measure is not absorbed or destroyed, but is in fact preserved after we make this measurement. And that allows us to make many independent, redundant measurements of the same photon in the cavity. And you can see a schematic of how we do that here, where we use this Ramsey interferometry type parity measurement, and we repeat this multiple times. So here's a quick example of this in action. In this case, we make something like 30 repeated measurements of the same photon. And you can see the signature of that, where the qubit flips back and forth here. And when we analyze this measurement record, we see with very high probability, there was 1 photon in the cavity. And most importantly, after we've made 30 measurements, we're extremely confident that there wasn't 0 photons in the cavity. And what we saw was not just a series of errors occurring. And most importantly, we've generated an exponential suppression of the detector-based false positives. So you can see this scale here is logarithmic. And the cost to us is only a linear increase in the number of measurements we have to make. And that's a trade-off we're always going to take. Okay, putting this all together, we need to characterize our ability to detect photons now. And that's where this plot comes in. So on the horizontal axis is the number of injected photons, the mean number of injected photons. And on the vertical axis is the mean number of photons that we count. So up here in this region where we inject a lot of photons, you see that we measure a lot of photons, and this happens with something like a 40% efficiency. But as we reduce the number of photons that we inject, we expect this to continue to fall off. But what we see is actually a flattening here. And this is our false positive probability, which corresponds to something like a few times 10 to the minus 4. And we know that these are not detector-based errors. That's exactly what we prevented by doing repeated measurements. But in fact, what we're seeing here is a residual background of real photons that live inside of our cavity. And we have lots of ideas of how to potentially reduce this number. That's not something we need to discuss right now. But the main takeaway here is that compared to what you would get with a linear quantum limited amplifier, this false positive probability corresponds to something like a 15.7 dB advantage over this quantum limit. And this, translating into a dark matter search, means that if you moved from a quantum limited amplifier to photon counting with this system, your experiment would be sped up by over a factor of 1,000. And that's exactly what we do. We put this into action by trying to do a dark matter search. Many of you might not have seen plots like this, but basically all the colored in regions are regions where a dark matter candidate is excluded based on experiments. And this purple region is where we've excluded it in this parameter space of the dark matter mass and its coupling to the electromagnetic sector. And you can see that this exclusion that we've made is extremely deep at this particular mass. Excuse me. And this is all due to the fact that we're able to count photons rather than having to measure both the incompatible pieces of information with our linear amplifier. And so we have plans of implementing this in future dark matter searches and potentially also in some quantum information applications as well. So with that, I'll conclude. It's been a really fun experiment for me to work on because I've been able to learn things about quantum information technology, but also apply them to a cosmology experiment. This 15.7 dB metrological gain that we've achieved will result in over 1,000 times speed up of dark matter searches. And we've shown that when we've been able to have unprecedented sensitivity to a particular class of hidden photon dark matter candidates. And you're welcome to check out our manuscript here and hear some of the people who fund this work and make this all possible. And with that, I'll conclude. Thank you very much.
Thank you for this excellent presentation. And so there's a question in the chat room. Would you like to answer that first?
Well,
I can read it to you. Is it a hypothesis that a dark matter will deposit a photon in a cavity, or is it a fact?
Oh, it's a hypothesis. That's something we're trying to test at the moment. First of all, are these dark matter candidates, do they actually exist? That's the hypothesis. And we've constructed these hypotheses in a way where if they exist, they would potentially also produce this photon in the cavity. But it's a hypothesis.
Okay.
Yes.
And here's another question. Is this work important to the quantum computing community? And if so, why?
Yeah, that's a good question. There are a few ways in which this can be related back to the quantum information field. The first is it's always good to have the ability to do quantum sensing and measure extremely small signals. I think this will be very important when we're trying to build large structures out of many qubits, and we'll want to know exactly what the state of the system is, and our ability to sense very small thermal populations or residual populations will be important in that sense to initializing our quantum computations. And this work kind of goes hand in hand with some of the work people in the quantum computing community are doing right now, where we're trying to figure out what are the effect of, say, cosmic rays or high frequency photons that are coming in and maybe messing up our computation or screwing up our qubits. And this kind of all fits into that picture, I think.
Any other questions? Thank you so much.
Yeah, of course.
So I just want to remind people that they can type in the chat or they can just ask the questions.
Yeah, this has really been fun for me because I actually came from the dark matter side of things, and I've been able to have the opportunity to learn about all the quantum information technologies and experiments and all those things.
Okay, well, thank you so much once again.
Of course.
Okay, here's another question. In the chat room, is there a spectrum associated with dark matter? Is it flat?
Well, it'll depend on exactly which hypothesis you're considering, but for the ones that we think about, because we know the dark matter is virialized with our galaxy, we know that it's gravitationally bound in our galaxy. We know that it actually looks like a radio signal, right? It's extremely sharp around the particular mass of the dark matter. And so these experiments are all like, tuning your radio just a little bit until you find the right signal. It's extremely sharp in neuro. Thank you for the question.
Okay, if there are no other questions, once again, thank you so much for this excellent presentation. And let's move on to the third presenter, Aaron Greenberg. Aaron is an undergraduate student at the University of Pittsburgh, where he majors in physics and mathematics. He researches with Jeremy Levy on the lanthanum aluminate strontium titanate interface and nanostructures created in it in his free time. He's a member of Pittsman Club, Ultimate Frisbee, and Club Archery teams. As far as the question about the dream employers. Next up for Aaron is the graduate school. He is planning on starting a PhD program in next fall. He did say that if you were to choose an industry location to work right now, it would likely be Oak Ridge or Argonne National Labs. So I'm going to let Aaron take it away and start his presentation. Please, Aaron.
Thank you, Adrian, for the introduction, and thank you for the invitation to speak here. As Adrian said, I'm going to be presenting today on the conductance of lanthanum aluminate strontium titanate nanostructures for temperatures between the freezing and boiling points of water. Lanthanum aluminate strontium titanate is actually quite the interesting material. It exhibits a large number of fascinating properties, such as a high mobility two-dimensional electron gas, which forms at the interface between the lanthanum aluminate and the strontium titanate, as well as a metal insulator transition, superconductivity, magnetism, tunable spin orbit coupling, and more. Returning to this high mobility two-dimensional electron gas, we see that its properties are actually strongly dependent upon the thickness of the lanthanum aluminate on top of it. And for thicknesses between 3 to 4 unit cells, the two-dimensional electron gas takes on a base insulating state, but it can be locally transitioned into a conducting state. We use this property to be able to create devices in the LAO-STO interface, and we've created devices such as electron waveguides, single electron transistors, nanocross devices, and many more. These devices are actually created through a technique known as conductive atomic force lithography. By applying a positive voltage to our atomic force microscope tip and dragging the positively biased AFM tip across the surface of the sample, we transition the interface from its insulating to conducting phase, and applying a negative voltage to the AFM tip, and by dragging the negatively biased tip over an area that's already been written with the positively biased tip, we're able to erase whatever we've written, much like an Etch-a-Sketch. This writing and erasure process is easily repeatable and does not damage or degrade the sample in any way, so we're able to use this one sample for many tests, over and over many devices. This lithography technique works through something known as the water cycle mechanism, where water in the air will adsorb onto the LAO surface where it dissociates into H+ and OH- ions. The positively biased AFM tip removes those OH- ions from the surface, leaving the H+ and then producing the conducting interface that we need for our devices. The negatively biased tip removes those H+ ions, which restores the sample's insulating state. However, due to loose ions in the air, slowly over time, the surface will become deprotonated, leading to a slow decay of any devices that we create. This self-erasure of the device begins as soon as the segment of wire is written, and it occurs over a timescale of hours. However, since our writing is typically done for speeds between 10 nanometers per second and 1 micron per second, this limits our ability to create complex and large devices. So the more we slow the decay and the more we're able to create stable nanostructures at room temperature and pressure, the more we're able to create newer intricate devices to do more interesting tests with LAO-STO. We know that we're able to slow the decay of a written sample by placing it into vacuum or dry gas, but you're not actually able to write a sample in vacuum or dry gases. We also know that by taking a sample and putting it in vacuum and cooling it down to very low temperatures, such as about 80 Kelvin, we're able to almost completely stop the decay of one of these nanowires. So, of course, this begs the question, how exactly does the temperature impact the decay of nanowires? So that's what I set out to test. In particular, I wanted to look at the regime above freezing, where first off, we wouldn't deal with any sort of condensation on the sample, but we'd be able to use modest cooling effects to potentially increase the lifespan of these devices. So to test this, we first write a device in an atomic force microscope. We then transfer the written sample to a cryostat, such as this quantum design PPMS, and then we vary the temperature at regular intervals, all while monitoring the sample's conductance, and this gives us the conductance as a function of both temperature and time. The first tests that we did focused on temperatures between 275 and 300 Kelvin. We did these tests in air on a nanowire written for 4-terminal measurement. The air that was used was actually sealed within the PPMS at all times, so there was no flow of air either. We used 1-hour time intervals for each temperature. That is to say, we began monitoring the sample at 300 Kelvin, and we allowed it to decay for approximately an hour. After this, we decreased the temperature to 295 Kelvin. We saw the characteristic jump in conductance that we see when we decrease the temperature, and then we allowed it to decay for another hour. We repeated this for 290, 285, 280, and 275 Kelvin. Then, to begin our data analysis, we actually applied a linear fit to each one of these time intervals, as shown by the black lines here. By taking this linear fit, this gives us a dg/dt for each temperature that we're able to use for our analysis. The first thing we did then was we actually took the natural log of this rate of change of conductance and plotted it against inverse temperature. This takes the form of an Arrhenius plot, which is governed by the Arrhenius equation shown here to the right, where the rate of change of the conductance, dg/dt, is equal to a rate constant times the exponent e to the minus EA, where EA is the activation energy of the decay function, over kBt, with kB being Boltzmann's constant. The slope of this line then is given by minus EA over kB, which can then be used to calculate the activation energy of the decay function, and we find that to be about 0.77 eV. This agrees with theoretical work done by Sanjay Adhikari in Cheng Sen's group at the University of West Virginia, where they say that they expect the surface proton hopping energy for LAO-STO to be similar to values obtained in water-only clusters, or approximately 0.7 eV. To find such good agreement with prior theoretical work was a very heartening result to find. The next thing that we did to further analyze this data was we actually took the average conductance for each one of those time intervals and divided it by the rate of change. This gives us an estimate for the lifespan of one of these devices, and at 300 Kelvin, we find that this lifespan estimate is approximately 1 day. Now, from our experience with creating the devices, we do know that after writing a device, it does take about a day for the device to decay to 0 conductance when held at room temperature and pressure. However, what we find from this graph is that by cooling the sample as little as 25 Kelvin, we're able to reach a lifespan of approximately 23 days. So a very modest cooling of the sample is able to create a very, very large increase in the device's lifespan. This has potential applications for doing things like sending samples that are already written to another lab which may not have the capacity to write samples, and for potentially writing larger and more intricate devices. The next set of tests we looked at was focused primarily on heating the sample. Again, this test was performed on the sample in air, with the air being held constant through the entire test. But we also added a 2-dimensional device to the schematic, this box here, to see if there was any difference in the decay between the 1-dimensional and the 2-dimensional device. As it turns out, there's no significant difference between the 1-dimensional and the 2-dimensional device, so we'll focus on the 1-dimensional here. We were actually interested in the heating of the samples because we wanted to know if this behavior that we see for low temperature, where an increasing temperature corresponds to an increase in decay rate, would continue for higher temperatures, and also because we had a potential collaborator ask if they could do an annealing in oxygen at very high temperature on a written sample and have the device written still survive. Furthermore, when high voltage is applied to a sample, if there's any sort of dirt on the surface of the sample, it could lead to arcing, which would lead to high temperatures, and we wanted to ensure that it wouldn't destroy the sample. So for this test, we again used a time interval of approximately an hour. And for low temperatures, we see that the behavior we saw in the previous test does continue to hold, where a low temperature corresponds to a slower decay. However, at approximately 340 Kelvin here, we begin to see an increase in the conductance. And what we found is that this is not actually the device conductance, but it's actually a global background conductance inherent to the sample that very quickly overpowers the device conductance by more than an order of magnitude. This background conductance is currently the object of more study, but it does prove to be fairly interesting so far. Continuing our analysis, we only look at the low temperature regime, and we're again able to calculate the activation energy for the decay rate, and we find it to be 0.67 EV, which again agrees with the theoretical work done by the group in West Virginia. So in summary, we have shown that a very modest cooling of LAO-STO devices can dramatically increase the device's lifespan, and doing so allows us to create more complex devices, and that in turn allows us to study new and interesting effects of the interface. Furthermore, learning about how LAO-STO behaves at high temperature will let us better understand the mechanisms behind the CAFM lithography, the technique that we use to create these devices, as well as potential properties of the sample, such as this background conductance. So with that, I'd like to thank you all for your attention and ask if there are any questions.
Thank you for this wonderful presentation. If anybody wants to write questions in the chat room or just ask them, please go ahead. If there are no questions, I mean, maybe there will be some. I don't know if you mentioned this or not, but could you say what the source of the global background conductance that you're seeing is?
Yes. So this global background conductance that we're seeing, it's not related to the device conductance. And like I said, it's currently the object of more study. Preliminary tests have shown that it's not actually dependent on the pressure of the sample. So it arises in both air and in vacuum and decays equally quickly in air and vacuum. Our current prevailing theory is that it's related to oxygen vacancies in the bulk STO substrate, but we are still looking to learn more about it.
Thank you. Anybody else has questions? Let's wait a little bit. Okay, well, if there are no questions, let me just remind everybody that Aaron is planning to go to graduate school. If any university professors are recruiting students, he is looking forward to start a PhD program in the fall of 2022. Okay, here's a question in the chat room. Can you see it?
Yes, I can. So someone asks, can you bias the proton hopping by applying a voltage between two 1D lines? Yes, you actually can. We use this effect to create field effect transistors and other devices in the substrate. So applying a voltage to one wire will allow you to do something like create a band gap in a transistor. And this effect we do try to take advantage of. Thank you for your question.
Let's wait a little bit more to see if there are follow-up questions or new questions, like 15 seconds or so. Okay, well, if there are no other questions, I want to thank Aaron one more time for this wonderful presentation. I'm going to move on to the fourth presenter for the day. And our fourth presenter is Abhishek Kumar. He's a PhD student at Indiana University here in Bloomington. He is working with Professor Babak Serajeh to study the non-equilibrium topology and dynamics of a driven quantum system. One aspect of his research also focuses on driven quantum phenomena that can be simulated on synthetic quantum simulators, especially ion trap platform. So the high school version of his research sounds like this. In physics, especially condensed matter physics, we try to understand the properties of matter. To do that, we look for experimental signatures that explain the properties of a matter. In our theoretical study, we have proposed a probe that could distinguish whether there is multiple or one ground state. Dream employers, IBM, Google Quantum AI, IonQ. All right, Abhishek, take it away.
Yeah. Let me share my screen. Yeah, thanks, Adrian, for introduction and for this opportunity. Is my screen visible?
Yes, you're not in the what's it called? In
Play mode. Yeah,
but we can see them. I mean, this works fine.
I'll just. Yeah.
Perfect now.
Just let me. Is this problem? Yeah. Thank you, everyone, for being here. So I'm going to talk about Floquet gauge pump, and this work has been done in collaboration with Professor Gerardo Ortiz, Professor Philip Riserme, and Professor Babak Seraje at Indiana University. And this work is, my presentation is based on this recent paper. Yeah. So before talking about the concept and its demonstration, let me talk about the motivation behind our work. So we know that in non-interacting topological system, we have something called bulk boundary correspondence, which means that corresponding to a non-trivial bulk topology, there exists some localized boundary states. And often in an experiment, these localized boundary states are considered as experimental signature for the bulk topology. But our understanding about interacting topological quantum system is very limited. And moreover, the notion of topology depend on the choice of local basis. But the degeneracy of many-body ground state does not depend on the choice of these local bases. So we need a probe that could detect the degeneracy of many-body ground states. And for that purpose, in this talk, I will be going to present a Floquet gauge pump, which is a dynamical probe, and that can detect the degeneracy of many-body ground state. Before going to the Floquet gauge pump, I will talk about the gauge pump. So gauge pump is a special probe, and it is constructed by considering the two gauge equivalent system. And then we connect these two systems through a bridge. And after gauge transformation, we can put all the gauge parameters into the bridge Hamiltonian. And then we look for a observable that depends on these gauge parameters. And one such observable is the gauge current. And we obtain a expression for gauge current like this. The reason the gauge current detects the degeneracy is that it is related to the basically ground state energy. So let's say the decoupled system is degenerate. And then if we add this bridge Hamiltonian, then this lifts, this addition of bridge Hamiltonian lifts the degeneracy of the system. And when we change the gauge parameter, the many-body ground states gets switched. Like here, you can see like there are two ground state, psi 0 and psi 1. If you change the parameter gauge parameter phi h, it will switch between 1 and 2. And this produces a discontinuity in the current. But when you have a trivial system, then there is a no degeneracy, And if you just add the bridge Hamiltonian, it will just lift the overall energy. There will be no switching from one state to another. So one example of this is the basically Josephson junction, where for the trivial superconductor, we have 2 pi periodicity in Josephson current, and for topological superconductor, we have 4 pi periodicity. So for Floquet gauge pump, we consider one system and then drive the left half of the system and right half of the system differently in a way that it can create a bridge within the system. So we don't require 2 systems. We just need one system and drive the system differently on left and right side. This drive can also provide some Floquet topological phase in the system. And in that case, if we calculate the Floquet gauge current, we get the expression like this. And moreover, if we just look for the time average Floquet gauge current, we see that this gauge current depends on the quasi energy. Okay, so to demonstrate this concept, we have considered 1D XY model with transverse field. So we take a static system with 1D XY model and with transverse field, and then drive the system on left side and right side differently. Then our overall system becomes periodically driven, and these are the drive parameters. Just remember this like theta HL and theta HR, which will be useful in our further discussion. So in a static case, we know that the XY model has two phases, ordered phase and disordered phase. In our ordered phase, we have 2 degenerate ground state. In disordered phase, we have only single degenerate ground state. So using our Floquet gauge pump technique, and by calculating the time average Floquet gauge current, we will try to detect these 2 phases. So for that purpose, first we have to calculate the Floquet Hamiltonian. So in high frequency limit, one can calculate the Floquet Hamiltonian, and there we get the Hamiltonian like this. And we have to notice that there are additional terms like this, which is Zielinski-Moria interaction. And this interaction is basically function of drive parameters. So by changing this drive parameter, one can change the Zielinski-Moria interaction. In general, it is very difficult to diagonalize a interacting spin model. So luckily, in this case, if we do the Jordan-Wigner transformation, then we can diagonalize the Hamiltonian. So Jordan-Wigner transformation is a non-local transformation that change the spin degree of freedom to a fermionic degree of freedom. So in fermionic language, when we get the Floquet Hamiltonian, we get 2 Kitaev chain, and there is a bridge Hamiltonian. And this bridge Hamiltonian is basically unconventional Josephson junction. Why unconventional? Because in a conventional one, we only have this hopping term. But now we have this additional pairing term, which is also there. So for this, we will calculate the gauge current. But before calculating that, we know that Kitaev chain has basically 2 phases depending on this parameter value, topological superconductor and trivial superconductor. And in 2 representation, basically the gauge group is here the U1 gauge and here the U1 rotation. And if we write the parity, which is basically in fermionic language, exponential of I pi times a number operator. And in spin language, it is the n point SG correlator. So we can see that this hopping and pairing phases related to this hopping and pairing term can be fully controlled by these drive parameters. And from these two plot, we can see that we can get a good range of hopping and pairing phases. So we also calculated the analytical expression for gauge current. In trivial case, we get the left and right gauge current like this. And this, so basically, if we had only conventional Josephson junction, we get this kind of only this term. But because the system is unconventional, we have this additional term, which is here. And just notice that this coefficients depends quadratically on hopping and pairing amplitudes. In this case, we have three processes of current, which are like Cooper pair co-tunneling, Cooper pair tunneling, and Cooper pair condensation. In topological case, we get the current like this. And here we can see that the current also depends on the parity of the system. And this second part is basically the usual Josephson junction or usual Josephson current. But we have additional term because of this additional term because of unconventional Josephson junction. So here we have this coefficients depends linearly on this WB and delta B. And the two processes are the Majorana quasi-particle tunneling and Cooper pair splitting. We have done the numerical calculation, and then this numerical calculation verify our analytical result. And we can see that in trivial phase, there is no discontinuity in the current. But in topological phase, we see that there is a discontinuity in the current, and which is related to the change in parity. So these plus minus values are indicating the plus the values of parity, plus minus one value of parity. So this work is not just the theorist's dream. It could be also implemented into trapped ion setup. And if and for trapped ion setup, we can consider the experimental value like this, and using this experimentally suitable parameter values, we have calculated the magnetization current. And in that case, we see that whenever in disordered phase, there is no discontinuity in current. But in ordered phase, we see that there is a sharp discontinuity in the current, and which is again related to the parity, and or you can say the n spin Z correlator. So this way, it could be detected in a trapped ion system. So by looking at the current, we can detect that whether the system is ordered or disordered.
Very good. How are
Okay.
you?
So in conclusion, we have proposed a Floquet gauge pump, which could unveil the ground state degeneracy of interacting quantum system. And we have also calculated the analytically and numerically the gauge current in unconventional Josephson junction. And the Floquet gauge pump can be experimentally realized in a trapped ion setup. Yeah, thank you.
Beautiful presentation. Thank you so much. Let's wait 15 seconds or more to see what questions we can get. Questions could be typed in the chat, or you just ask them. Anybody can ask the questions. Just unmute yourself and ask the question. So let's see questions. Okay, so I'm not sure that you have said this or not, but what kind of interactive interacting spin systems could you probe with a Floquet gauge pump?
So thank you for the question. So basically, the requirement for the usefulness of a gauge pump is that there should exist some gauge group, and apart from that, there should be no interaction between the basically a spin which is perpendicular to the magnetic field and parallel to the magnetic field. So what I mean by that is that, let's say if your magnetic field in SG direction, then if you have any additional interaction, like let's say SG, even you have the n spin interaction, this could be useful to probe the degeneracy of those kind of system. The only thing is you should not have interaction like SG-SX or SG-SY. But as long as you have interactions which are only which avoid this condition that SG-SX kind of interaction, we can probe that system. And it's not only the two spin, it's like multiple spin also.
Thank you. There's a second question in the chat. You want to read and then answer it? Read it and.
Yeah, sure. What technological implication can be impacted by this research? I think at least from the research point of view, the thing is that a lot of times we do not have a good probe for the understanding of basically whether the system is topological or trivial, especially when the system is interacting. So this is basically a probe that could detect whether the system has some topological property or not, or even in more general, you can say that whether the system has the ground state degeneracy or not. So technological, I am not quite sure, but I think it will be good to see. I mean, it can be simulated on trapped ion. So a lot of things are like, if you want to see that whether some system has some degeneracy in ground state for a quantum simulator platform, it could be used. But how that will lead to technology, I do not have much idea, I'd say, at this point of time. But if one can integrate this like quantum, basically trapped ion quantum simulator into some digitized version, then yeah, like this could be like, this will be in the background where you can use this technique to understand whether the ground state of the system has degeneracy or not. And then you have to convert somehow that into the digitized mode. But I don't know, this is just my speculation. But physics point of view, this is like a kind of, it's always good to have more probe to detect the different properties of material, and especially for interacting quantum system, this will be a good probe, we hope so.
Okay, well, thank you for your answer. And if there are any follow-up questions in the chat or spoken word, please go ahead. Anybody with questions? All right, so I'd like to remind everybody that we are experimenting with a new format. All the sessions before were from 3 to 4. I mean, for 1 hour, 4 times 15 minutes. And we started a little bit earlier. Everything is recorded. It's going to be a longer recording, but we're going to post it online. We ended up with almost 20 minutes per presenter. This is supposed to end at 4:30. It's now Eastern. It's now basically, let's say 4:15. What we would like to do in the next 15 minutes would be to open the floor to everybody. People can ask questions. Anybody can ask anybody any kind of questions. I want to remind everybody that our goal is to connect, to better connect students with industry. And one project that we're working on right now, I looked through who's here. For example, Patrick Vora from George Mason is one of the leaders in that area. We haven't started for good, but NSF has a program called Intern, where if your professor is a PI on a grant, NSF will give you $55,000, I think, so that you could go in industry and intern in a place. I'm not sure exactly how the connection is made or the matching, but that's what we're gonna figure this out in the next 2 months. I also want to, so there are options that are supported by third-party entities like NSF, so that you, with all the work that you've done and the knowledge, be connected with people who truly need your talent. And remind a question from the very beginning where Avinash was asking. So I'm gonna address these questions, these 2 questions. I'm gonna read them again, and then let's see what kind of discussion we get. But this is specifically addressed to industry partners. These are questions that Avinash wanted to have answered. What pathway do the industrial partners have for postdocs to transition into research and development of their companies? And are there any postdoctoral research positions at the companies? So maybe this would be a good start, or the NSF intern program. So with this, I'll open the floor to everybody who wants to say something.
So Adrian, do you want to just restate the question is mainly, do industrial postdoc positions exist? And how should we go about hooking our students up with them?
So the first question was, if you are a postdoc and you want to start working in industry, how do things happen in a company so that the postdoc doing research transitions to research and development in that company in general? That was one question. And second, if you could say something about the NSF intern program, even if you restate what I said or maybe formulate it better, that would be meaningful. Thank you.
Well, I'm able to say something, I guess, about the NSF intern program to some degree, in that we're all still figuring it out. But it is basically exactly what you said. You know, a lot more young scholars like yourselves are choosing to forego the traditional academic route and go into industry. And, you know, I kind of view it as a try before you buy situation for the company, where using this supplement from the NSF, the company can have you on there for a 6-month period to kind of get to know you, see how you do things, and see if they want to employ you. And even if they aren't able to, you then have that industry experience that so many people want you to have when you go out on the job hunt. Anyway, so it seems like a very nice way to go about smoothing that transition from a purely academic environment to one where you know, you're operating in a more industrial space. It would be great if any industry people on the call can share their perspectives on the other side of it about this intern program. Adrian called me out at the start of it, so I'm just paying it forward to somebody else.
That's pretty good. We could ask Charles. He always has an answer. How are you, Charles?
So I wanted to make sure that I let everyone know that the IBM internship program specifically in quantum is available for young people who want to get involved in quantum computing at IBM. And so I want to share with you kind of, Google the kinds of opportunities that we have. And so here's a job for Quantum Developer Summer Internship Program that came out 3 days ago. It is for a PhD candidate type person or an intern that want to get involved in the IBM Q network and the KISS-KIT community. And so you can apply obviously at IBM.com. There's opportunities out there for IBM research at the TJ Watson Research Laboratory. As a matter of fact, I saw some folks on this call that are from that laboratory. As a matter of fact, Mark Ritter, who is on this call, started the IBM Quantum program. And he's a senior researcher at IBM. And so you have folks who are researchers here that are looking at your work, paying attention to what you're doing. And I'd ask that you guys go off and apply for those research internships and send me your contact information. And then there was one other thing I wanted to share with you guys. I know we talked about postdocs, and I know Patrick Voris from NSF. We also have partners here who, let me see if I could pull this up. We have partners here, and I don't know if you guys can see this, but I got this information from our DOE partners as a part of the QED-C. Besides NSF, and NIST, there's opportunity here from the DOE as well. And so if you look at this, DOE has a comprehensive internship program as well. And it's not insignificant in terms of scope. And it starts from May to August. Now this year is probably a little late to get engaged, but here's some of the eligibility requirements. If you guys want, I can pass this to any one of you guys. I'm gonna drop my email in the chat so you can have this information. I guess the only thing I'd share is with the work that I've heard today, most of you are extremely talented and probably would not have any trouble finding work. And I'll just leave it at that. Thanks, Adrian.
Charles, can I ask a quick follow-up question?
Sure.
So, a lot of the times when we talk about internships for either graduate students or postdocs, there are these great official channels that already exist that we can go through. But with this NSF program, this NSF intern program that I'm still now just getting familiar with, and maybe somebody else on the call has more experience with it or having used it in the past, but is that a way to I guess essentially, do we jump around when we advise our students about using these intern programs from the NSF? Do they have to kind of do a double thing, right? Where they and their advisor need to get the NSF supplement first, and then they have to go through the IBM competition process. How can we make it so that this program works well and kind of speeds people into the industry positions? Like, do we need to find a list of industry mentors who might be willing to partner with an interested professor and their student / postdoc for this? What do you think is the most realistic route?
Well, one of the things that the NSF program provides is it provides the funding level for these students to get engaged in an industry perspective. And so one of the things that we do at IBM is we have that intern program that we fund. And so, at the end of the day, I think that having a tighter coupling of the NSF program is probably a little bit easier for us because, we get we get a lot of resumes, and it's a very competitive process to go through the normal IBM internship program. And so, you know, part of the challenge and Bradley Holt will be on the call, our next TAC meeting, to talk about these things next month on the 22nd. We're going to have industry perspective on better ways that we can work and best practices that we can work on. And we're going to invite the students to that, Patrick. That's our next session, our next workforce TAC meeting. But you're right. I think that there needs to be a tighter coupling between the NSF program and the professor. The challenge that we're faced with here, and most of the challenge with this in the quantum group, is that the trajectory, you know, we have so, you know, every company has such a limited amount of resources from a research and development standpoint that, you know, having these mechanisms that is more predictable will be more convenient for them. I mean, to have a guy like Mark Ritter, who created the quantum program and actually created the IBM's role in QED-C, is a big deal, right? And so, you know, because he understands all of the technical aspect of most of this research, having spent all his years at the T.J. Watson Research Laboratory. So, but not everyone will have that understanding. And so the process, and I understand some students may be a little frustrated about the process, you know, before you can talk to a person that actually understands, you know, topological bulk materials and concepts that we talked about today, you may have to go through a process where, you know, just finding the right person to be able to convey that is not easy. And so Patrick, your question is well understood. I just think that, you know, just today we talked about 4 or 5 different research areas, and so QED-C's role is to try to bridge that gap. So the answer is yes to your question. You know, we should look at the National Science Foundation program and identify the specific researchers with the professors through this mechanism. Probably is a best way to do it. And to establish the program directly. But quite frankly, it should be not just IBM and every other quantum company to include Sensors Network.
That's an important point that you're making. IBM is big, IBM does everything. Everybody should follow what IBM is doing, good role model for everybody. But what I wanted to clarify is that we have a lot of small companies which also need interns. I wanted to clarify another aspect, that it's now end of June. And I think Celia would like to make an announcement that we've worked this out, whatever we are saying right now, in such a detail that by, say, the next plenary, which is in September, that we have a process in place. It's about 2 months. I think the meeting next month is the 20th, not the 22nd. We'll invite the students. I also want to give an opportunity to the 4 presenters today. If they have questions, they will say something or ask our industry partners before we disconnect. But you are now on a list of student presenters' talent, right, that industry needs. And we're going to keep you informed. I don't know that you know that there is a matching process in the medical profession. It's a very complicated matching where people, before they start the residency training, they visit and then they indicate what hospitals and universities they would like to attend. And then the universities are going to submit a list of who they want as residents. And then there's a big algorithm with matching. We can't do exactly that, but if we had something that would be towards that, we would be thrilled. And that's what we're trying to do. And that's why what you hear today is not completely clear, because we just started. We started about 2 or 3 weeks ago, established a set of steps such that by September, when we have plenary, we would be able to announce to everybody that we have a very clear set of steps for everybody. As far as the presenters today, do you have any questions that you want to ask everybody or anybody?
Yeah, I have a general question, like, are there opportunity for the, let's say, the simulation kind of things? Like my field is time periodic Hamiltonian, where you have the spin simulation that one can do on the quantum computer or whatever, like a digitized version of quantum simulator? Are there like are there company or
so you're talking about electron spin experiments, or are you talking about I'm trying to understand, Kumar, exactly what you're asking. Go ahead. Can you repeat that?
It's like simulating the spin models, basically qubits, let's say a spin half system.
Mm-hmm.
So you have, but now so is there an opportunity in that direction if the system is basically not just the static, but let's say, as I presented, like some sort of varying in time, the parameter is varying in time.
Mm-hmm.
So is there a way where the physical phenomena, especially time-dependent physical Hamiltonian, we can simulate on those kind of, or quantum computer, or?
So the answer to your question is, for spintronic capabilities, there has been plenty of research in that area, even at the T.J. Watson Research Laboratory, and primarily, obviously, at many different laboratories around the area. There's simulation of those things that are being done today from a physical standpoint, trying to model some of that. But just as a modality for compute, clearly there's many folks that are working on that. I just heard him talking about, the lithography process and creating bulk material that will help with that. And so, the answer is yes. To think about spintronics and the way that these orientations of electrons or whatever fermions that you have is something that's being experimented upon in industry and obviously in a research world writ large. So what I have for you, Kumar, is we usually keep a repository of every research paper that has been done from an experimental standpoint on the IBM quantum computer across all genres of research. And that experimentation repository that we offer out to the world is available. And so what I will do is, if you contact me, I will give you the link for that. We use Airtable, and it'll have all of the research associated with what's been done on the IBM quantum computer, and then we can look specifically through that database to see if there's any experimentation on spin qubit simulation on quantum machines, right? So, I mean, spin electron.
Yeah, and what I'm going to do, I'm going to take the question, I'm going to work out with Abhishek a formulation. And since not everybody's here today, we had like between 20 and 30 people today, I'm going to send it to everybody that received an invitation and all the industry members, and then see what they respond. I mean, at some point we need.
It's huge. It's over 500, 600, 700. It's a large number of research papers. A lot of those research papers that have been done on the IBM quantum machine has been from our Q network members. And the Air Force. And so what you can see from that, Kumar, is exactly the breadth of what has been done on the quantum computers to date. And a specific problem, that use case that you talked about, which is simulation of spintronics, or, in a more granular way, trying to understand the nuances between the many body problems associated with that. There are folks that are working on that as well. And we're in talks with engaging researchers that are looking at those problems. An example would be a young lady over at the University of Rhode Island. She's a many body problem person, and she's looking at that as well. And so we do joint research from an IBM standpoint in some of these engagements with quantum, And so those things are being looked at. So now the answer that you want to know is which papers are out there for that specific area of interest. And I'll commit to you, Kumar, that I'll give you that link and we can go through that. All right.
Yeah, thanks a lot. Yeah, that will be, I will also formulate a formal question or kind of proposal.
Yeah, you got my email there. You got my email there.
Yeah.
Akash?
Hey, yeah, this might be a little bit unrelated, but I kind of wanted to understand a little bit more about what are some of the research thrusts that are happening at the national labs, because that's something I'm also interested in looking into. So I know there might be some people here who work at national labs. I have a little bit of experience with Fermilab and Argonne because they're in the area, but I'd like to learn a little bit more about what quantum information related work is happening, but also will be happening in the next 5 to 10 years, where I'll be potentially joining. Maybe this is something we could do offline as well, but I would love to hear from the representatives here.
So Akash, I can chime in and I'm gonna let somebody else talk, but that same research list of papers that I mentioned to Kumar have research papers from Oak Ridge, National Laboratories. We have 3 hubs. One at there's 3 other national labs that are publishing actively based on an IBM engagement that they have for hubs, and in all of those ranges, material science and anything you can think about under the sun in terms of what they're doing. But that repository has all of their papers in it too. And I'm just going to pause there and let somebody else talk about what other groups are doing.
Thank you. Yeah.
Okay, so any other questions? We are now 4 minutes past the time when we were supposed to stop. So let's see if we have other questions.
I'll say just one quick thing to Akash also for looking into this stuff. Akash, there are a number of nationwide centers, one of which you know about, Chicago Quantum Exchange. And most of these are tied in quite nicely with national labs and will let you see an overview of what work is going on there.
That's a great idea. Yeah.
So if there are no other questions, I want to thank everybody for spending time with us today, the 4 presenters mainly, and everybody else who found the time to come and join us to listen to the presentation, answer questions, and give answers. Thank you so much. We will see you next time. I hope you have a wonderful rest of the day. Bye-bye.
Thank you. Bye.
Thanks for organizing it all, Adrian. Take care.
Thank you.
Hey guys, if you want to hang around, I'm getting ready to have that link right now. In 1 second, Adrian, I'm going to pop it into you right now. All right.
Okay.
Somebody send it to me. The young man asked for it, just dropped off. I want to make sure he got it.
It's okay because we're still recording, so we're going to just share the recording with them.
All right, here it is. I have it here. So I haven't tested it, Adrian. So let me make sure that it works here. But
you're gonna put it in the chat, or you're gonna share the screen
right now. I'll put it in the chat. Paper summaries. This is a paper summaries. I think she got the right one. I got a very thorough person that helps me.
I see it.
And let me just see, let me see if it works. This is the paper summary for all the research papers that someone has published. And there's only 10 records here. It should be
with IBM, right?
Yeah, there should be over 500 of them. I'm only seeing 10 here. Oh, this is one company.
Right, but if there was some,
right?
Exactly.
So I think the way it works is if you click on there, you put a company in, and then I got to figure out how to work. So one of the problems is the guy asked me about many body problems, basically about electron interaction, for different polarized states of spin, right? Or different spin states. And so that simulating many body dynamics on current digital quantum computer is an example of exactly what he was asking me. It's like the 3rd one down, right? And so his thought process about what he wanted to do with it was exactly what it is. And so there's some level of understanding that, I hate Airtable, by the way, because every time I go there, I'm looking for something, I can't find it. But all of our papers are published out there with our Q network members. And what that will allow that young man to do is go in there and read what they did, and then he can use it for his own experimentation using the same logic, because they post the code oftentimes when they do the simulations on our machine. They put the Python code in the papers. And so he could just basically take that and then apply his specific use case. And looking at his experimentation, he's the one that had the little bridge between the two posts, and it was running the different electron states on the other side, and basically trying to replace the middle piece. You know what I mean? That's what he's trying to do. The Indiana University guy, your school. And so what he's working on, I understand, and maybe can't articulate it as well as he do, but it's pretty clear in my mind. And so that paper, that one first page, shows Samsung doing the same thing, right? So
okay. But is Airtable just for IBM? What if it's a smaller company, or what if it's D-Wave or IonQ? Would that be in Airtable, or it would be in a different system?
So we use Airtable for all of the folks that we engage with our IBM Quantum Network. So as an example, you notice if you look at this link, right, you see Samsung. And so Samsung, if you go there, let me see if I can just share it with you.
Yeah.
Every one of our research programs that we have, some in joint research, some in, all right, let me see if I'm not sure if I'm showing you my screen here, but let me just share my screen here. So part of the outcomes of let me see if I can share it. Here it is. Part of the outcomes in our IBM Quantum Network is either we have different agreements. So some of them, most of the access agreements that we have, here's an example of one of our partners, Samsung, right? And they published papers based on the access that they do. And some of it is public and some of it is not. And we have a public-facing Airtable where some of that public stuff for all of the folks' experimentation on the IBM quantum computer is located. So anybody can access it and read it, right? And so it's just for the IBM access for quantum computers, not for everybody. So for example, if you push this button, it gives you a link to the title and the link of where they published it, right? And so, and this is 2020-07, and Samsung published the many-body problem experimentation, and here it is. And so they talked about, their specific experimentation on the IBM quantum machine and what they did, for example, in this case, quantum chromodynamics between quarks and condensed matter physics. And so what the guy asked me was, quantum spin chains. That's exactly what he asked me about, right? And so here's the experiment of a specific client, that did that exact same experiment. And so what I want to show that young man and hopefully you guys are still seeing me, but let me just see if I can go back to where I was. What I want to show that young man is that information is out there. Unfortunately, I can't get to everybody in the world to show them how to eat, but I want to make sure that you and me, Adrian, we pass that information on freely. That's the kind of information that I provide to clients all the time, but that thing is also growing crazy. And so you have it, it's there. Now, the students should be able to figure out how to work it, right? It's just a query.
No, I will give it to him.
Yes.
Yeah. And then I'm going to he said he's going to put together a formal question that is a,
I think I got enough
way of asking, so there's no ambiguity and whatnot.
Yeah, I think
no. For you, it's totally fine.
Yeah, I think I got enough.
We want to ask everybody.
I think one of the things
if D-Wave, for example, are they, because
they track their own problems. I mean,
but I'll send him.
Right. So in the commercial industry, the research that's done, depending upon the type of research that is being done, the companies themselves decide what they want to do, whether they want to publish it in open source channels or not. And what we provide is a way that we can coalesce all that together if they choose to. And most of the work is experimental, but some of the stuff is their own proprietary work and they don't want to share that. But for where we have circumstances where they want to share it, we provide, at least for our clients, one place you can go to and see all of what it is. And then there's a set of that for the whole world, because most of IBM is going at this in a democratized way. And so the whole idea of building a quantum network is to have everybody learn from one another. And so that information is available. It's just that you got to know that it's out there. Most people don't know that it's out there, right? And so, instead of this guy finding one paper on many body problems and electron spin, right, ensembles of many bodies and electron spin, and then looking at the bottom of that paper and then trying to figure out how to connect to the rest of them, it may be useful for them to go to a site where they're all, at least from a quantum perspective, from an IBM perspective, all right there. I can just go through that in a search.
Okay.
Mm-hmm. All right.
Thank you so much for the information I want to share with you.
Yeah, and then the other thing.
Anything else from anybody else?
Yeah, anybody else? I see Mark stayed on this to the end. Mark, I don't know if you know Adrian. Adrian and I are the Workforce TAC vice chairs, but Mark Ritter, Adrian, started the IBM Quantum Presence primarily in government. I mean, he started the program. And so you should know Mark. And I want to solicit Mark to help me figure out a coupling mechanism for what they were talking about with the NSF, because one of the things we want to do, Adrian, is make it easier for these young people, right?
Yeah.
Anything else?
Oh, that's it. Thank you so much for your help today. And
yeah, I've been running.
All right. Bye-bye.
All right.
Thank you.
Call me sometime so we can organize, Adrian. We haven't had a chance to chat.
Yeah. How about, yes, I will call you soon, but next 2 weeks from this last Thursday, we'll get to see each other again with Celia.
Okay.
Right?
Right. See you later.
All right. Bye-bye.